So, at its absolute core, anemia means your blood has a low oxygen carrying capacity. The best way to think about it is this. Your red blood cells are like a massive fleet of delivery trucks, and oxygen, that's the critical package they have to deliver to every single cell and tissue in your body. Anemia is what happens when that essential delivery service starts to fail.
And that's the real question, isn't it? Because a delivery service can break down in all sorts of ways. Maybe you don't have enough trucks to begin with. Or maybe the trucks you have are built all wrong. Or what if they're being taken out and destroyed before they can even make their delivery? Each of these is a different kind of failure, so let's explore them one by one.
Okay, let's start where it all begins, the factory. Your bone marrow is this incredible factory just constantly churning out red blood cells. But, just like any factory, things can go wrong on the assembly line. And that's our first big category of anemia, the production problems.
Think about it. Every delivery truck needs a sturdy container to hold its cargo, right? Well, for a red blood cell, that cargo container is a super complex protein called hemoglobin. And to build that hemoglobin, the factory absolutely has to have one key raw material: iron. It's simple. No iron, no cargo containers.
And this is where it gets really interesting. When the factory is short on iron, it doesn't just stop. It tries its best, but it ends up making these smaller, paler red blood cells. Doctors have a name for this. They call it microcytic anemia. They can actually measure the average size of your red blood cells, what's called the MCV. And a low number is a classic sign that the cells are missing that crucial iron building block.
All right, let's imagine a different scenario. What if the factory has all the iron it needs, piles of raw materials, but the assembly instructions are messed up? What if the blueprints for putting the cell together are corrupted? Well, that leads us to a totally different kind of production problem.
This is a perfect example of how two different factory problems can have opposite results. We just saw how a lack of iron gives you small cells. But if you're deficient in vitamin B12 or folic acid, that messes with the cell's DNA maturation, the actual blueprints. The assembly line gets stuck, it can't finish the job right, and you end up with red blood cells that are way too big, what we call macrocytic anemia. So, same factory, different issue, completely opposite outcome.
And there's another production flaw, but this one is literally written into your genetic code. It's called thalassemia. Here, the blueprint for the hemoglobin protein itself is faulty from the start. The factory is missing a critical component like an alpha or beta globin chain. So just like with iron deficiency, you can't build enough proper hemoglobin, and the result is, you guessed it, small microcytic cells. It really shows you why doctors have to dig deeper. Both conditions lead to small cells, but one's a nutritional issue and the other is genetic. Totally different ball games.
Okay, let's switch gears and move on to our next category. What happens when the factory is actually producing the right number of cells, but they roll off the assembly line with a fundamental design flaw? They are just structurally unsound from the get-go.
A healthy red blood cell has this amazing, flexible, donut-like shape that lets it squeeze through the tiniest blood vessels. That shape is held together by an internal protein skeleton, with key parts called spectrin and ankyrin. Well, in hereditary spherocytosis, there's a genetic mutation in those proteins. The cell's skeleton is weak, so it can't hold that disc shape. Instead, it just defaults to a sphere.
And being a sphere is a huge problem. Spheres are rigid, they're not flexible. So when these round cells get to the spleen, which acts like the body's quality control filter, they can't squeeze through the narrow passages. They get trapped. The spleen's immune cells see them as defective and just destroy them. This premature destruction is called hemolysis, and it leads to anemia. It can even make the spleen get bigger from all the extra work it's doing.
Now for one of the most famous design flaws of all, sickle cell anemia. And it all comes down to this one tiny error. A single mistake in the genetic code for hemoglobin. A single amino acid, glutamic acid, gets swapped out for another one, valine. That's it. It seems almost impossibly small, but the consequences, they're enormous.
And here is the fascinating and terrifying part. That one little swap causes the hemoglobin molecules to get sticky and linked together, forming these long, rigid rods. But, and this is the critical part, it only happens under one very specific condition, when the red blood cell has dropped off its oxygen. And that trigger leads to this devastating chain of events. A red blood cell does its job, delivers its oxygen, the faulty hemoglobin then polymerizes and the whole cell gets forced into this rigid crescent or sickle shape. These stiff cells can't flow anymore. They create logjams in tiny blood vessels, which blocks blood flow, starves tissues of oxygen, and causes episodes of just unbelievable pain called a vaso-occlusive crisis.
So, we've looked at problems with production and problems with design. But what if you have perfectly made, beautifully designed red blood cells, but they're being lost or destroyed by forces outside their control? Well, that brings us to our final category.
The most straightforward cause of anemia is simply losing blood. It's called hemorrhagic anemia, and it's what happens when you lose red blood cells faster than your body can possibly make new ones. It can be sudden and dramatic, like from a major injury, or it can be slow and sneaky, like a stomach ulcer that's constantly weeping blood. Either way, the end result is the same. There just aren't enough delivery trucks left in the fleet. Now, what if the entire factory just shuts down? That's essentially what aplastic anemia is. It's not just a red blood cell problem. It's a total, catastrophic failure of the bone marrow. And as you can see here, that means all the cell lines are affected. You get low red blood cells, which causes anemia. You get low white blood cells, which puts you at high risk for infection. And you get low platelets, which leads to serious bleeding problems. This widespread failure of everything has a name: pancytopenia.
Let's talk about a more subtle kind of destruction. You know, a red blood cell's own metabolism actually creates these damaging molecules called reactive oxygen species. Healthy cells have a built-in antioxidant shield to handle them. But what if that shield is defective?
This brings us to G6PD-H deficiency. The G6PD-H enzyme is absolutely critical for keeping that antioxidant shield strong. Without it, the cell is basically defenseless against its own toxic waste. Those reactive oxygen species attack and damage the hemoglobin, causing it to clump up into these little blobs called Heinz bodies. The spleen sees these damaged cells and, you guessed it, pulls them out of circulation and destroys them, leading to another type of hemolytic anemia.
So, as we've seen, getting from a genetic flaw or a nutritional lack to a full-blown crisis, well, there are a lot of different ways to get there. The big takeaway is that anemia isn't just one thing. It's really a whole collection of stories, each one about how one of the body's most critical systems can fail.
Let's just quickly recap with our delivery service analogy. We talked about iron deficiency, which is like the factory running out of raw materials. Then you have sickle cell, where the trucks themselves literally change shape and cause massive traffic jams. We saw aplastic anemia, which is like the entire factory just shutting its doors. And hereditary spherocytosis, where the trucks are built with a faulty frame destined to break down early. 4 completely different ways for the same system to fail.
And in the end, that's what it all comes down to. Understanding the specific type of anemia, the why behind the failure, is everything. It's what guides the diagnosis, explains the symptoms, and determines the treatment. From a factory shutdown to a single misplaced amino acid, the sheer variety of these conditions is just a powerful reminder of how incredibly complex and sometimes fragile our bodies really are.